Okay, for example number 13, we're going to be talking about the limit of a recursively defined sequence. We want to investigate the sequence of the set of a subscript n defined by the recurrence relation. So if we're given the first term where a subscript 1 is equal to 2, and then the sequence formula is a subscript n plus 1, which is equal to 1/2 times the quantity a subscript n plus 6 for when n is equal to 1, 2, 3, and so on. So let's explore what happens when we're plugging in the values of n. And we're going to plug all the values of n all the way up until 9. Well, we first know that the number in the first sequence when n is equal to 1, we know that a subscript 1 is 2. If we let n equal 2, then we have a subscript 2, which is going to equal 1/2 times the quantity a subscript 1 plus 6. And so a subscript 2 is going to equal the following. It'd be 1/2 times what we got for the first term plus 6, which ends up being 4. If we set n is equal to 3, then we're going to follow the formula. A subscript 3 is going to equal 1/2 times a subscript 2 plus 6. And what we got for a subscript 2 was 4. So we get 1/2 times 4 plus 6, which is equal to 5. When n is equal to 4, we end up following the same format, and we end up getting 5.5. When n is equal to 5, we can see that that term of that sequence is 5.275. When n is equal to 6, we get 5.875. When n is equal to 7, we get 5.9375. When n is equal to 8, we get 5.96875. And when n is equal to 9, we get 5.984375. So there's a reason why we continue to see what was happening once we got to at least 9. At the beginning, we can see we're going from 2, 4 to 5, and then what's happening is this sequence is increasing, and it's approaching the value of 6. So for step 2, we can say that the sequence suggests it's increasing and approaching 6. Now to confirm, we want to be able to use mathematical induction. Okay, so in order to use mathematical induction, we're going to show that a subscript n plus 1 is going to be greater than a subscript n for all values of n being greater than or equal to 1. Now for when n was equal to 1, we know that a subscript 2 was going to be greater than a subscript 1, meaning the second term was greater than the first term. And that's true because 4 is greater than 2. So let's assume that n is equal to k. So here we're going to be using mathematical induction. On the left side, we have a of k, a subscript k plus 1. On the right side, it's a with a subscript of k, and we have a greater than in between them. So on this side, what our original function tells us, or what our original sequence tells us, is that we're adding 6. So what induction allows us to do is to be able to add 6 to both sides of this inequality. Okay, and then after they add 6, then you can see it's being multiplied by 1/2. So therefore, now we can multiply both sides by 1/2. So on the left side, we can then say that a subscript k plus 2 is going to be greater than a subscript k plus 1. So by induction, we can then say that a subscript n plus 1 is greater than a subscript n for when n is equal to k plus 1, so for all n. And in step 7, we then want to verify that the sequence a subscript n is bounded by showing that a subscript n is greater than 6 for all n. So we know that that first term is less than 6 for when n is equal to 1. So now again we're going to use induction. We're going to show that a subscript k is less than 6 for when n is equal to k. So we have a subscript k, which is less than 6. And again, going by the original sequence formula, we can add 6 to both sides. So we end up getting a subscript k plus 6 is less than 12. Then, again, from the sequence formula, we're going to multiply both sides by 1/2. So we end up getting 1/2 times the quantity a subscript k plus 6, and half of 12 is 6. So we know that this on the left side is less than 6. And therefore, we proved that a subscript k plus 1 is going to be less than 6. So by induction, we can then say a subscript n is less than 6 for all values of n. Now, since the sequence is increasing and bounded, the monotonic sequence theorem guarantees that it has a limit, so meaning that it's convergent. So the theorem doesn't tell us what the value of the limit is, but we do know that when L is equal to the limit as n approaches infinity of a subscript n exists, we can use the given recurrence relation to write the following. So in number 11, here's our limit as n approaches infinity of a subscript n plus 1, which was equal to the limit as n approaches infinity of 1/2 times the quantity a subscript n plus 6. Factoring out the 1/2 and then taking the limit of this, we would then say that we have 1/2, the limit as n approaches infinity of a subscript n from here tells us that it's going to equal L. And that's how we get L here, and then plus 6. Now, for example, for step number 12, since a subscript n approaches L, then a subscript n plus 1 also approaches L, as n approaches infinity and n plus 1 approaches infinity. So in step number 13, now we can write this down as a formula. We can say that L is going to equal 1/2 times L plus 6. This represents L, and that was what our limit is equal to, so it's saying it's equal to 1/2 L plus 6. And then we can find out what that L is going to represent, or solving for L. So here, we're going to multiply both sides by 2, and then subtract L to both sides, and we end up getting a value of L that is equal to 6.